All right then, let's please see now this example that we were looking at the other day. And like I say, polynomials are really the easiest objects to talk about when you're coming up with, using calculus to sketch these things. We'll look at the function we looked at in class the other day because I ran out of time a little bit at the end of that class. We got f of x equals 2x cubed minus 9x squared plus 12x minus 3. Now, I want to remind you that back in pre-calculus, for instance, what I'm saying is you need to come into this class already knowing that this third degree polynomial with this positive leading coefficient, its end behavior is down on the left, up on the right. As well, even though I'm probably not going to do it right now, if it came to finding the x-intercepts of this thing, you'd look for the rational x-intercepts by taking factors of the constant term over factors of the leading coefficient and doing repeated synthetic division until you found those x-intercepts. And then you would get like kind of a rough sketch about what this polynomial looks like. For now, I'll just say it waves around for a while and then does its thing. But there's a lot you can do with pre-calculus that I'm not really covering right now. Maybe I will in a future video, maybe I won't. But I want to get to the calculus of this thing is we'd like to find the intervals of increase and decrease. That's where the first derivative is either positive or negative. And we'd like to find the intervals of concavity. That's where the second derivative is either positive or negative. We want to find the local maxes and mins. I'm not going to write that because I'm kind of out of room. And we want to get a sketch, in which case you would need things like x-intercepts, y-intercept, and everything, put it all together. So as we get on to the solution for some of this, I want us to what's called find the critical numbers of f. That, or those I should say, is where is f prime 0 and where is f prime undefined. That's what the critical numbers are talking about. So then let me call this step 1, what we're doing here. Let's take f prime. Pretty easy case to do with a polynomial. We got 6x squared minus 18x plus 12. Let's set it to 0. And, you better be able to factor ax squared plus bx plus c. Like, all these skills that you were supposed to dial in your algebra, they're going to keep on coming back to haunt you. They're not going to go away. You got to factor ax squared plus bx plus c. And you got to do it toot sweet. Here we can see we can just take a 6 out of this first. And now we're looking for factors of 2 to add to negative 3. And so this thing's going to be 0 when x equals 2 and when x equals 1, right? These are called the critical numbers. Once you've got the critical numbers, you want to stick those. Let me see if I can do that a little bit over to the right here, if I'm going to have enough room. I don't know how this is actually going to render on YouTube. What you want to do now for our, let me just say this was all step 1. For step 2, I want to play what's called the first derivative test. This is a real common kind of thing. It's in every calculus textbook. And what you want to do is you want to choose test values. I'm going to show that in a moment. And then, test f prime for either positive or negative. at those test values. So what I want to do then is get a number line, stick my critical values on there. Here's 1 and 2, my two critical values. Let's test a number to the left of 1. Something to make the arithmetic easy there, since 0 is in the domain of this thing, is choose 0. You got to choose numbers that are actually in the domain of the function, of course. And with a polynomial, the domain is all real numbers, so we don't have to sweat over that too much. In between 1 and 2, we could test 1.5. And then something to the right of 2, we could test 3. So I'm testing these values into the factored form of the first derivative. Let me tell you something. This positive 6 that's out in front, it's not going to make any difference on the positive negativeness of it. Because if the first derivative is positive, actually, here, I'll just do it like this and maybe say this later. We're testing 0 into the factored form of the first derivative. Well, the 6 is always going to be positive. 0 minus 2 is negative. 0 minus 1 is negative. So we got a positive times a negative, which is negative, and then the negative times a negative is positive. Here, I'll do this kind of like what I did in class the other day. This positive is from the 6. This negative was from the x minus 2, and this negative was from the x minus 1. Positive times a negative is negative, negative times a negative is positive. So what we've learned right here is everywhere to the left of 1, we could have chosen any test value. We could have chosen negative a half, 0, or excuse me, we could have chosen a half, 0, negative a half, negative 1, 2, 3, 4, right? It doesn't matter. You can think about that on your own. But what we found is the first derivative is positive everywhere to the left of 1. So since the first derivative is positive, that means that the function is increasing. So in other words, the function roughly looks like this to the left of 1. Now at x equals 1, x equals 1 was one of the critical numbers. This was one of the numbers that causes the first derivative to become 0. So I know that at x equals 1, the tangent line is horizontal. So the graph looks kind of flat like this for a moment. Now let's test 1.5 into the first derivative. Well, we got the 6, which is positive. We got 1.5 minus 2, which is negative. And we got 1.5 minus 1, which is positive. Okay? This came from the 6. This came from the x minus 2. This came from the x minus 1. Positive times a negative is negative, and negative times positive is negative. So in that interval between 1 and 2, didn't matter what test values you chose, the first derivative now is negative. So when the first derivative is negative, the function is decreasing. So roughly speaking, it looks like this. Now at x equals 2, see, we're done inside this interval. We're done at 1. We're done at this interval. Now we're at 2. Well, at x equals 2, this was a critical value of the function, causing the first derivative to become 0. So we know the tangent line looks flat there. In other words, horizontal tangent right there. Now I'll go to my test value 3, and I'm using that factored form of the first derivative. I got the 6, which is positive, 3 minus 2, positive, 3 minus 1, positive. This came from the 6, this came from the x minus 2, this came from the x minus 1. Positive times positive times positive is positive. So what we found now is everywhere to the right of 2, the first derivative is positive. When the first derivative is positive, the function is increasing. The first derivative test is quite powerful because we've got the general shape of the graph. If you remember, we had already said up above from our pre-calculus, we were expecting this thing to go down on the left, up on the right, wave around for a while in the middle. See how it goes down on the left, up on the right, waves around for a while in the middle? But we're getting more details now, because now we know that the top of this is called a local max, right? This is a local max right here. And we know its x value is 1, and the y value we can find by going back to the original function, not the derivative. if x were 1, then this is 2 minus 9 is negative 7. Negative 7 plus 12 is 5, and 5 minus 3 is 2. I'll always double check my calculations so I don't do, let some stupid thing go through. If x is 1, then this is 2 minus 9, which is negative 7. Negative 7 plus 12 is 5. 5 minus 3 is 2. So we know this local max is right here at 1, 2. It gives us a lot of information. See, we didn't get that information in pre-calc. We knew that, the function went up and came back down, but we didn't know where the top of that hump was until we used calculus. Similarly now, this guy right down here is a local min. Just locally it's a minimum. We're not claiming that it's the minimum of the whole graph or anything like that, but just locally around that area, it's the bottom of a trough is what I call it. The x value is 2. Now the y value is going to be just a little sneakier. I'm not sure if I can do this in my head so easily now. We got 2 cubed, which is 8, and 8 times 2 is 16. 2 squared is 4. 9 times 4 is minus 36. 12 times 2 is 24. So we got 24. We got minus 36 plus 24. That's 6 and 6. That's minus 12. 16 minus 12 is 4. 4 minus 3 is 1. So really that's just some scratch work to do in my head. I should probably double check it. We were looking at putting 2 into the function because we want the y value. We're not talking about derivatives. We're talking about the y value that goes along with the x value too. So 2 cubed is indeed 8. 8 times 2 is 16. 2 squared is 4. 4 times 9 is 36, and it's negative. 2 times 12 is 24, and we got the minus 3. So we got 24 minus 36. So that's going to be 6 and 6. That's minus 12. 16 minus 12 is 4. 4 minus 3 is 1. Yeah, this local min here is at 2, 1. I'm just going to erase this because it's not really, it was kind of some scratch work that I should have done on the side, but I was just too lazy to do that. And don't you do that when you're turning in scratch work to me, because I don't want to have to pick through all your cat scratch trying to figure out like what's the work and what's the scratch. Make it neat, make it presentable, or use eraser tape and get it out of my way. So we've got a lot of information now about the shape of this graph. Now the last thing we need to do is we need to figure out where are the inflection points. The inflection points, that's where the graph turns concavity. See how it's concave down here and it's concave up here? Somewhere in between x equals 1 and x equals 2, there's an x value where this thing changed from being concave down to concave up. And that's what we got to do now. So for step 3 then, we want to use the second derivative for what are called the intervals of concavity. So then we're going to need the second derivative, f double prime of x. Polynomials, this is going to be an easy game. 12x minus 18. So this is how we play this game now. We take the second derivative, we set it to 0. So here again I can let me see, did I do this right? 12x minus 18. We can take a 6 out of here again. 2x minus 3, right? Use eraser tape. Don't give me a bunch of scratch outs. It's not fair. 12x minus 18. So this is going to be 0 when 2x minus 3 equals 0. So we'll add 3 and divide by 2, and x equals 3 halves. This is our only candidate for an inflection point, is 3 halves. And most likely it's going to be at 3 halves, right? That's 1.5. By the way, it's really just coincidence that I chose 1.5 up here as my test value. I was just choosing a value equally between 1 and 2. Another thing is you can't always just assume that the inflection point is going to be halfway between the local maxes and local mins. That won't always be the case either. It's just a simple kind of example. It's the first example we do, so it's like everything just works out really nicely. What you want to do now is once you figure out where the second derivative is 0, we're going to play a similar game to what we did with the first derivative test. Let me slide this paper up there a little bit. But this time, we're playing with the second derivative. So now we've got the 3 halves. We're going to choose a value to the left of 1.5, for instance, 1. it's okay that that would happen to be a critical value of the function, because I'm not checking into the first derivative. I know the first derivative would be 0 at 1, because it was a critical value of the first derivative. But I can just choose values that are in the domain. 1 to the left of 3/2, I could have chosen 0, would have been an even easier one, quite honestly. Now I can choose 1 to the right of 1.5, for instance 2. Now I'm going to stick these values into the factored form of the second derivative, and this is going to tell me about concavity. So the 6 is positive. Let me slide that up a little bit more here. When I stick 1 into this, 2 times 1 is 2, 2 minus 3 is negative. Positive times a negative is negative. So this gives me the conclusion. By the way, should I write in here like I did before? Since a lot of you are beginners at this, this positive came from the 6, this negative came from the 2x minus 3. And we said positive times a negative is negative. So look, don't make the mistake that I see a lot of students make. Up here when we were doing the first derivative test, this was about function increasing, decreasing, local maxes, and local mins. When you're using the second derivative, you're finding about concavity. Remember, concavity is kind of like cup up or cup down. So when I've got that the second derivative is negative, that tells me the function is concave down. And so the way I'll usually sketch that is I'll literally just put kind of like a downward looking cup right there to the left of 3/2. The function is concave down to the left of 3/2. So now I'm going to go to the right of 3/2 with my test value 2. And I'm going to, got the 6 is positive. The 2 times, I'm going to stick 2 into the second derivative. 2 times 2 is 4. 4 minus 3 is positive. See, I don't care what the value is. I just want to know if it's positive or negative. This positive came from the 6. This positive came from the 2x minus 3. Positive times a positive is positive. When the second derivative is positive, this is telling me that the function is concave up. So I know this function is concave up. Now look, this video has been going on a while. I want to see if I can wrap it up here. But let me tell you something. We got a lot of information here. We got a really lot of information, okay? Let me write some of it down, and then we'll actually write the sketch for this thing. This function is, we can get all that without even looking at the sketch. It's increasing wherever the first derivative is positive. Well, it's increasing from negative infinity to 1. You don't really include the 1 because it's not actually increasing at 1. It's just up, it's increasing up to 1. And it's also increasing from 2 to infinity. You got to be able to write that in interval notation. You got to be able to do it correctly. This is all just like pre-calculus stuff that people stumble over because they're not, putting in enough time to just practice stuff that they're not sure about. F is decreasing from 1 to 2. Not including the 1, not including the 2, because it's not actually increasing or decreasing at those values. It's just decreasing between them. Now, F has a local max at 1, 2. F has a local min at 2, 1. And now it's about concavity. F is concave up. Now we're looking at the second derivative, and it's concave up from 3/2 to infinity. And it's concave down from negative infinity to 3/2. Because this is a polynomial, so I don't have to really sweat too much that it goes all the way out to infinity. And the other thing is, remember how the inflection point is where the thing changes concavity? This thing has an inflection point. See how it changed from concave down to concave up right there at x equals 3/2? So the inflection point is at 3/2, and now I need a y value to go along with the 3/2. It's going to be just a little awkward because I got to stick 3/2 into this function. So let me just kind of do the scratch work right here for a second. I got 2 times 3/2 cubed minus 9 times 3/2 squared plus 12 times 3/2 minus 3. Because I need the y value, so I'm going into the original function. I'm sticking 3/2 into this thing. 2 times 3/2 cubed minus 9 times 3/2 squared plus 12 times 3/2 minus 3. Oh, so this is going to be a little bit of a pain. So we got 27/8. This is 27/8, and 2 times 27, this is 54/8. This is 9/4, and then 9 times 9 is going to make 81/4. This is 36/2, or I could have done 12 over 2 is 6, and 6 times 3 is 18. Minus 3. Let me check this now. This is 27/8. 27 times 2 is 54. So this is 54/8. This is 9/4. 9 times 9 is 81. This is minus 81/4. This was 12 over 2 is 6, and 6 times 3 is 18. Okay. So the 54/8, we can write that as 27/4 minus 81/4. And then 18 minus 3 is 15, so plus 15. See, these are the little bits of arithmetic that people goof up and get these things wrong. It's a real shame because you kind of knew what you were doing, but you got sloppy on your arithmetic. 81 minus 27. 11 minus 7 is 4. 7 minus 2 is 5. This is negative 54/4. Right? Because 81 minus 27. 11 minus 7 is 4. 7 minus 2 is 5. This is negative 54/4 plus 15. This is 25, 26, 27. This is 27/2 plus 30/2, right? Negative 27/2 plus 15. So this is 30 minus 27. This is 3/2. It's just a coincidence that the y value is equal to the x value here. 30 minus 27, this is 3. This is 3/2. The y value here is 3/2. So then, this inflection point is at 3/2 comma 3/2. And you need all this information that we've done. Now let's see, this has been a long video. Let's see if we can get this sketch down, and get moving out here. Here's a y-axis. Here's an x-axis. Here is 3/2. I would just say something like this. See how the local, just so we can make a nicer, quicker sketch here. See how the local max is at 1, 2? Let's put 1, 2 right up here. And so this thing's coming up like this. Down, and then it's coming down to 2, 1. And it's going up like this. So here's the local max at 1, 2. Here's the local min at 2, 1. Here's where it went from being concave down to concave up. That was right here at 3/2, 3/2. And that's everything you need to know about this thing. There's the polynomial. It's increasing from negative infinity to 1, and from 2 to infinity. It's decreasing from 1 to 2. It's got an inflection point at 3/2, 3/2. It's got its local max, its local min. Really, that was just the simplest thing you can actually do, believe it or not, with these things. It's just a very simple polynomial. I would probably not even ever test you on something quite that simple. We got to do a much more interesting example in the next one.